So, hi Laksha, you can hear me, right? Hello? Yeah, okay. So, how are you doing? Everything is going fine? The classes and all? It's okay, no problem. In fact, I'm also not very well today. I'm having a little cough, so I'll be taking what is very small session. So, if you have any confusion, you can ask me in the next session. Today, I'll be just teaching, giving a flashback of week 7 class and just discuss the assignment questions. Okay, we can start. I think nobody else will join, only you are there. So before starting a session, as always, we have to, give a flashback of week 7 classes, how what is being taught by in the week 7 by Professor Tomar. So basically, he started with a concept and topic of radiochemical separations. What happens in that? This is a chemical separation of radioisotopes or radioactive elements, and it is a unique resolution in terms of Z and A. And what is the need? Pure radiochemicals for application in medicine research are vitally important. That's why the separations is needed. Radio tracers for application in industry, healthcare, etc. Study of short-lived radioisotopes and chemistry of heavy elements for uses in many industries. Okay, especially the energy industry. And then he talked about the basic principles of radiochemical separations, the carriers, holdback carriers, scavengers, separation time, radiochemical purity, radionuclide purity, specific activity, and radiochemical yield. Basically, the important thing is carriers and scavengers and the radiochemical yield. This is the percentage separated in desired radiochemical form. And then he talked about the fission products of and how we can deduce it from a modern periodic table, and the methods of radiochemical separation. So there can be many methods. First one is precipitation, and it could be direct precipitation. It is used for elements like rare earths as fluoride, or, or SrNBA, or Ag as AgI. Oxidation state adjustment, example cerium and zirconium as iodate, reduced to cerium 4 to cerium 3 to separate from zirconium 4, because cerium 4 and zirconium 4 cannot be separated. And then isotopic exchange with pre-formed precipitate is false fast separation, cerium silicotungstate or technetium tetraphenyl arsonium perchlorate. And then he talked about basically solvent extraction. The basic principle of solvent extraction is, example, you have M aqueous plus L organic giving Ml organic. The distribution coefficient, we know D is equals to C organic over C aqueous. Separation factor S between a solute A and B can be given as dA by dB. So the examples are fission product, iodine separation. It reduces all iodine species to I negative using thio uh, ion, which oxidize to I negative to I2 using Br2, and solid extraction of I2 into CCl4. Uranium or Pu separation, aqueous phase, and a common extraction are HD, EP, TBP, TTA, topo, diethyl ether, MIBK. And you know why these are used, topo and all these all are used in, in various methods. Some are used as a surfactant, some are used as, for synthesis of nanocrystal, etc. So it becomes important to, separate them. Remember this, why this solvent extraction is used. There is a question in the assignment regarding to this. Okay, moving further is a ion exchange. It is a partitioning of solute between stationary phase and mobile phase. Cation exchange, where there is a cation which exchanges, example RSO3 minus H plus M minus. It reversibly gives RSO3 minus and M plus, where the M minus M plus is exchanged to X plus. Example is thorium from uranium, Dovix and an exchange reagent plus uranium giving thorium, and you see uranium is held up. It is used in the separation of individual rare earths. And then he talked about extraction chromatography. We know very well that there is a stationary phase in the chromatography, there is a mobile phase, Here generally a complexing agent solved on inner support is a stationary phase, but a mobile phase is H plus and OH minus, etc. Examples are separation of zirconium and hafnium using 95 Jadar and 181 HFS tracers. Extraction chromatography column is tricapellyl monomethyl ammonium chloride on styrene or dimethyl benzene elution with 8 molar HCl plus 2 m HCl. You can read this paper. It is a very good paper if you are more interested. What are the details of the extraction chromatography? Then there are certain fast radiochemical separation, gas jet transport system, pneumatic carrier facility, and in fast chemistry what we have, it is basically in a Dhruva reactor. We can see PCF as a Dhruva reactor, and this is for hydride volatilization. Example antimony, SN or TE, isotopic exchange with performed precipitate solving extraction and proton radiation in air. Then we have automated rapid chemistry apparatus, which is ARCA. It is gas jet transport plus HPLC, and this was actually basically discovered by Trotman in 1995. Atom at a type of chemistry, which is generally alpha or gamma ray spectroscopy. So what is the basic principle? PET, radiochemical separation units. What happens? There is a nucleophilic substitution of F18, precursor is mannose triflate, and the catalyst is cryptoflix, and this is used for biological imaging. Okay. Then in the lecture 2 he talked about the radio tracer concept, for which George Hevesy got the Nobel Prize in Chemistry in 1943, and this is just basically radioisotopes have identical chemistry as the stable isotopes, so they can be used to trace the path of an element. Example in industry, environment, medicine, agriculture, etc. So it can be used as a diagnosis of diseases by imaging in vivo and determination of hormones in vitro. So determination of trace quantities of analyzed metallines, biological molecules, etc. Remember, the radio tracer can be used as in vivo and in vitro. That means in situ also. For example, if you're doing some experiments of killing bacteria, or anti-cancer drug, or the fate of the drug or protein or amino acid, you can do some in vivo study and you can do some in vitro studies using these radio tracers. There are some advantages: sensitivity and simplicity and low cost instrumentation. Precautions are mass defect, we know, unexpected oxidation state of tracer and stable isotope should be same, and radioactive daughter products, because we know they keep on converting into daughter nuclei. Then there is this, like we have titrations in our experiment in bachelor's, we have radiometric titration, and example is determination of chloride in a solution. Example AgNO3 plus NaCl gives AgCl plus NaNO3. The titration of Cl minus using 110 Ag labeled AgNO3 can be used. Example determination of CNS minus, WO42 minus, Mg2 plus, etc.
Hello, 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 hello.
Yeah, tell me, Akshay.
I've connected from a mobile since my microphone from the laptop was not functioning properly,
Okay.
and I have a few doubts.
Regarding this class or the last class?
This class.
Yeah, okay. Tell me.
So should I ask it now or after we finish covering to the material?
I mean, it will be better like you have doubts regarding the assignment.
I have doubts regarding the assignment and something related to the material.
Okay, so it will be better you ask after it finishes. Why?
Okay,
Because
sure.
it will be covered up. Okay. So basically, the concept of solvent extraction, and basically example is determination of the microgram quantities of mercury or lead, and in this radio tracers the basic principle is this only, we know distribution ratio C aqueous over C organic. Remember all this, and solvent extraction with radio tracers can be used for evaluation of solvent extraction equilibria and determination of stability constant of metal ligand complexes. So there is ion exchange separations, separation of trivalent actinides AM, CM, VK, CF, etc. and discovery of Mendelium analogy with lighter lanthanum homologs. Now, the most important method is isotope dilution analysis, and this is for use for determination of concentrations. There is no need for quantitative separation. A standard solution of a radius tracer is taken, and which has a specific activity as S and quantity as M. Now you add an inactive analyte Mx whose measured specific activity is Sx. Now it is conserved. So by the law of conservation, Mx plus M into Sx should be equal to M into S, which was the initial multiplication. So Mx can be found from here. Mx equal to M of S over Sx minus 1. So example is determination concentration of cobalt in a 10 ml solution. Suppose you have a standard solution of 60 cobalt whose counts is 340 counts per million. So S is 45.3 cpm per mg. Now you add it to a 10 ml of unknown cobalt solution. Now you can separate the cobalt by electrodeposition, where 10.3 milligram of cobalt whose counts are around 178 cpm. So concentration of cobalt in a solution will be like this. So this method you can use as isodilation analysis. Then application of IDA is you can find out the blood volume in a human body. Suppose you have 1 ml of patient blood, you label with for 24 NaCl and whose T half is 14.9 hours. Now let the specific cavity activity is 20,000 counts per million per ml. Now inject 1 ml of this IV. After 15 minutes, take 1 ml of blood and measure the activity. Let the activity be 4 cpm per ml. So 20,000 cpm per ml into 1 ml. This formula that we use, this one, we use this formula, and 20,000 cpm per ml into 1 ml equal to V plus 1 ml into 4 cpm per ml. From here we can calculate the blood volume in a human body equal to 4,999 ml. So like this we can find out the application of IDA. Now there is radio immunoassay. It is used for determination of minute quantities of substances of clinical interest in biological systems. The principle is substoichiometric isotopic dilution method. Ag is antigen, Ab is antigen specific antibody. Ab is very less than Ag. Okay. So basically, you know the concept of radioluminescent assay. So it is used for determination of minute quantities of substances of clinical interest in biological systems. Now the principle is substoichiometric isotopic dilution method. So you have an antigen Ag and you have an antigen specific antibody Ab. Now suppose this Ab is very less than the Ag. So the Ag is labeled with a radio tracer and you can find out the bound activity. So this is how it is used for a determination of minute quantities of substances of clinical interest in biological systems. Now there are certain application of RIA. This is assay of thyroid related hormones T3, T4, TSH, the blood things that we do, and hormones of reproductive system, example both protein hormones and steroid hormones. Differential diagnosis of hypothyroidism, neonatal hypothyroidism by mass screening of newborns of T3, T4 and TSH. Assay of tumor markers such as thyroglobulin, prostate specific antigen, alpha fetoprotein and carcinoembryonic antigen for diagnosis of cancer and screening of the patients. These are the application of radioimmunoassay. Now then there is radioactive dating, which is of use of archaeologists. You have a read over this, how this is used in geochronology, in carbon dating. It is very famous, which is used for the dating of fossil wood, leaves, leather, bones, clothes, paper, and the tritium dating is used for the water bodies. Now in the third class he talked about the nuclear analytical techniques, which are mainly neutron activation analysis and INV analysis, and the most important is neutron activation analysis. Neutron activation analysis was also found by Hevesy. It is simultaneous multi-element determination in diverse matrices. So you have a highly sensitive this availability of high flux nuclear reactor and high efficiency HPGE detector. So as many as 70% of the elements in a periodic table are amenable to neutron activation analysis, and it has application in many fields such as biology, geology, environment, forensic sciences, archaeology, medicine, and nuclear technology. Then basically this is the data that you can see how this sensitivity and all is changing by NAA. What is sensitivity? It is count per second per unit mass. It depends on theta, sigma, phi, detection limit, Curie law. You go through them. And then there are certain methodologies of NAA. The absolute method, elemental method, from counts directly. From there you can find out the CPS, and the relative method, which is a comparative method. And so it is by the Coval irradiation of the sample with multi-elemental standard. Now there is a single comparator, which is a K-naught method, where a Coval irradiation of the sample with a mono standard is done. Example: gold, manganese, and scandium. Then I think in the last class we talked about the application of NAA. NAA has many applications in geology to biology to environment to nuclear technology to chemical science to healthcare to archaeology to forensic science to material sciences. He discussed mainly the archaeology, how you can find out the characterization and origin of certain things by irradiating it with gamma, which is gamma spectrum of an incident pottery sample. And then some archaeology sample he talked about, and then he talked about its application in forensic sciences and how this was used for solving Napoleon death case. And Napoleon hairs has high amount of arsenic. So what happened, you have a look over the class. And then the forensic site analysis, like when somebody shots a gun, so the powder remains in the hand and you can find out this powder, barium and antimony, are present in a gunshot residue, and that also can be analyzed by NAA, which is used as a standard method to identify the shooter or the criminals. Then in food and nutrition, many elements at trace levels play a vital role in biochemical and enzymatic processes important for human health and diseases. The deficiency or excess in elemental concentration disorders and diseases need for controlled balanced diet, toxic elements, example arsenic, mercury, chromium, lead and selenium. Though selenium is known to be essential, but at higher concentration it is highly toxic. So the permissible levels in water are 10 nanogram per ml, and the recommended for daily intake is 50 to 150 microgram per day. So this is how it is applicable for food and nutrition. And then there is arsenic. Arsenic also have a safe limit of drinking water as 10 microgram per liter. Now AS2O3 has shown remarkable therapeutic efficacy in patients with acute promyelocytic leukemia, methylated AC, AS anti-cancer activity. Now AS induced carcinogenicity is greater than 40 countries in the world, and toxicity affects almost all organs, causing damage and dysfunction. The source of arsenic can be drinking water, air, food, occupation, and other environmental sources. So yeah, then you go through this, how it can be separated, iodine in food sample, the soil science, how selenium is essential, cracking of the nails if there is excess selenium, and rough skin is there, which is keratosis pilaris, cracking of the hooves, excess of selenium, and how it can be detected. Results of INAA in the food like wheat grain, wheat musk, mustard, rice, soil, etc. In the last class, he talked about ion beam analysis. So you have a low energy ion beam from where you get a backscattered projectiles, gamma rays, X-rays, and forward recoils, which is ERDA. And you can use this Rutherford backscattering spectrometry, whose principle is a precise relationship between energy of scattered particles and the mass of the scattering atom. So between the probability of scattering and the jet of the targeting atom, you measure the energy with respect to the mass number, and number of scattered particles gives you the concentration. So these all is important. Now why there are back angles in low energy ions? difference in particle energy is scattered from different M2 is maximum at most backward angles. Mass resolution is best at most backward angles. And then you can find out and what is unique about RBS. So it is used for depth profiling of a high jet impurity in a low jet matrix, and it is used for depth resolution delta x, where FWHM is divided by the differentiation of energy over x, and FWHM is generally detector energy resolution, and d by dx is a stopping power. From here you can find out the depth resolution. Now let me show you the application in this form. What is depth resolution? Suppose you have a thick target, you having tm th like this, and these are the counts, and these are the energy of different radiation. Now you are irradiating the ion beam by this much energy. Now you get this count. From here you can calculate the backscattered ion yield, and in fact you can even trace the ions. Example, characterization of polymer inclusion membranes. This is where cellulose triestate, nitrophenyl octyl ether, and dionyl naphthalene sulfonic acid. The depth profile of a metal ion PIM by 5 mega electron volt beam, and this is an AFM image. You can see different contrast showing the different element present here. So as we can see, depth profiling of cesium diffusion in a borosilicate glass also has an application. And from ERDA you can actually find out the stoichiometry. Let's see how can we find out the stoichiometry. Suppose we are using the ERDA in a reflection mode. Now you have the silicon nitride, which has high hardness, good creep resistance, and high wear resistance, low coefficient, and increased mechanical strength. Now suppose we irradiated it with until 20 nanometer. Now till 20 nanometer we have this much nitrogen and this much silicon. Now we correlate the counts of silicon versus nitrogen, and we can actually tell the stoichiometry as Se3N4, and the depth resolution is nearly 2 nanometer. So this is how it can be used to find out the exact stoichiometries. So this is how it works. Now going forward to your question, Lakshya, that are you there, Lakshya? Okay. So basically, as far as my knowledge is
Hello,
concerned, as far as my knowledge is concerned, Lakshya, uh,
hello,
yeah, you can hear me. Hello.
hello.
Yeah, you can hear me.
Yes, you're audible. Am I audible?
Yeah, you're audible. So basically, as far as my knowledge is concerned, Lakshya, this
Yes.
Mendelevium was, it was actually discovered by Dmitry Mendeleev. Okay,
Okay,
the guy of periodic table, and somebody is trying to join. Just a minute.
okay.
Yeah. So basically, it was discovered by Mendeleev only, which was the father of the periodic table of the chemical elements. And this is a 9th transuranium element in the actinide series. If you see the actinide series, let me show you the periodic table. Where let me search it here.
During the lecture, Professor Tomar mentioned that there was an analogy drawn between the lighter homologs of the elements preceding Mendelevium, and therefore there was a clue that Mendelevium will exist. But I was not
Yeah,
able to exactly
yeah,
understand what is.
exactly what happened. What happened? This was there. This was this element was there. Stenium was there. Okay, and then when stenium was bombarded with alpha particles in a high cyclotron facility, so we got a new element which is Mendelevium. This is how it was
So you have to,
discovered, and
yes,
this is a method which is still used nowadays in order to make Mendelevium. Like there is no other way like you can find out Mendelevium. You had it, stenium, stenium 253, and you bombarded it with an alpha particle, the helium nuclei, in a cyclotron facility, and you get Mendelevium. So this was used by Mendeleev. So this is why it was named as Mendelevium. But this is how it is still used. So this was an analogy, as far as I know.
okay, the analogy is from Einsteinium.
Yeah, Einsteinium. This.
Okay, got it. That is atomic number 99.
Yes, exactly.
Okay. But I thought the analogy will be from TM. I think it's tellurium or I don't know what it is, but
No, no,
atomic number 69.
it is Einsteinium only. Einsteinium.
Okay, that is a lighter homologue.
Yeah, yeah, it is like 5f13 and 7s2. But remember that there are also many isotopes of meldenium available. It is
Okay.
256, 257, 258, 259, and 260.
And
Okay.
these are the isotopes of Mendelevium.
Yeah, meldenium. But trust me, like uh, I mean, they have different half life. For example, some has an hour, some has in day, and some has in days. So
Okay.
as far as I know, this is how it is. I mean, when this astinium was bombarded with alpha particles in a Berkeley radiation laboratory in cyclotron facility, it was discovered. This is all I know
Okay.
about it. Okay.
Yes.
Yeah, and as far as your this assay is concerned, it's in radiochemistry. You know what is an assay? It is basically how I can say you can say it is just a method for measuring the activity. For example, suppose you're trying to measure the activity of dihydropyrimidinase. There is an enzyme DHP in a human liver homogenate. So
Okay.
it is a radiochemical assay. So this is how it can be defined. Basically, it provides a sensitive means to detect, analyze, and determine the kinetics. In you can say, if even if you're so example, suppose some method uses gold standard data for the preferring method of investigation. So
Okay.
basically, this is an assay, and I mean, it is used to test the quality basically. The literal meaning is to test the quality of. So, if so, example, if you're talking about a radiochemical assay, and if it, I give you an example. Suppose you are measuring the activity of DHP in a human liver homogenease, then you will use a radiochemical assay. So, an assay is a process that analyzes a substance to determine the composition or quality. Simple. And if you talk in terms of medicine, an assay is an analysis used to determine the presence of a particular substance and its concentration. So,
Okay.
in radio assay, we can include like Professor Tomer taught about radio immunoassay or other
Yes.
saturation assay, example bioassay technique, or and the most important thing, what is important about radiometric assays. They can be used to detect the analyze and kinetics of both biochemical and cell based formats. So
Which based form?
cell, CELL, cell. So
Okay.
suppose,
Cell based what?
yeah, so for example, you want to do some cellular studies. Suppose you want to find out something in mitochondria, or I mean, some deep biocellular studies. You can use
Yes.
this radio assay. So they can give you an exact information about, like, suppose you suppose this osmosis is not rightly happening in certain cellular divisions. It can be find out using these assays. So there are many
Understood.
bioassay techniques which are there. So the Professor Tomer just gave a just short hint about like how it can be used. You can read more. It's very interesting, actually, very interesting.
Okay. Sure. And can you repeat the general definition of an essay? I couldn't hear you clearly that time.
Okay, so we can say that in short, um, you can say it is a process that is used to analyze or determine the composition and quality of a substance.
It's a process.
Yeah.
Okay. And in the case of radiochemistry, is it a process or is it a chemical
Mm,
substance?
See, assay is a process. When you're using radiometric assay, that means
Correct.
you are using a radiometric process to test the composition and quality. Okay,
Okay.
example you will solve when you will see the assignment. No, there is a
Yes.
question. I guess. Uh, just a minute. I have not added it, but you can read here. Professor has actually told that how this radio immunoassay is important.
Okay. Also, I have another doubt.
Hmm.
It is related to the isotope dilution analysis.
Hmm.
In normal chemistry or in general chemistry, like we were taught in high school
Hmm.
up to 12th grade, so
Hmm.
there is a law of dilution.
Hmm.
And so, is this? Can you say that the same law can also be valid in the
Yes,
case of
exactly.
radio?
Isn't it the same thing? You see, only the terms are different.
Correct. Even I on one side of that equation shown on this slide, it looks similar to the equation used in general chemistry, but
Hmm.
on the other side, it has a different form. So I wanted to check with you.
No, no, that's okay. Example, you can remember this m1 v1 equal to m2 v2. Okay. Now
Correct.
m1 v1 plus m2 v2 equal to mv.
Correct.
Okay. Now here you are changing. You have some initial things m and s. You are changing it as mx. So mx plus m into s plus sx. This is
Yes.
do ms. So it is the same thing. It is the same thing. You try to correlate the analogy. This is
Understood.
same thing. Same thing.
Also, it in one of the slides it was mentioned that there is a technique which is a substoichiometric isotope dilution analysis. I
Hmm,
think
hmm, hmm, hmm.
I don't remember the name of the technique, but I wanted to check what is a like is it like substoichiometric IDA? Is there anything like supra stoichiometric IDA?
See, basically, see, IDA is a radiochemical method. It is used for measuring the mass and quantity of an element in a substance. Now, it involves adding knowing amount of radioactive isotope of the element of interest to a sample which contains an analyte. Okay, now there is a
Okay.
sample and there is a tracer which are homogenized. Now, there is a portion of the analyte which is then isolated in high purity from the sample, and the ratio of the isotope in the sample plus standard is then measured using this. So basically, you can say the sub-stoichiometric analysis is generally referring to the addition of the reagent to the sample in insufficient quantity, which may cause a full reaction. Are you able to understand what I'm trying to say?
Can you please repeat if you don't mind?
Okay, so see, isotopic dilution is regarded among chemistry measurements for the highest metrological standing because it employs signal ratio instead of signal intensity. So what
Okay.
happens? What happens in a substoichiometric analysis? It generally refers to the addition of the reagent to a sample in insufficient quantity, which may cause a full reaction. See what is happening. What is happening? Idea what you are doing. It is a radiochemical method for measuring the mass and quantity of an element in a substance. Now what happens
Correct.
here? You you add a known amount of a radioactive isotope of
Okay.
element of interest which contain an analyte, and then you find it out. Now when you're talking about stoichiometric analysis, it is generally adding the region to a sample in insufficient quantity, and which will result in a
Okay.
full reaction. So this is what stoichiometric dilution means.
Okay.
Yes.
How will it? My question is, how will it result in a full reaction when there is insufficient reactant?
No.
There will be excess of the target material atoms
Yeah.
or molecules.
See, you have to add a known amount. You see, in idea, you add a known amount of radioactive isotope of the element of the interest for a sample
Okay.
which contain the analyte. So a certain portion of the analyte is isolated in high purity, and from that separation you can find out the whole concentration. So you need not to have the full ratio metric thing. If you can
Okay.
isolate a certain portion of the analyze in a high purity form, from there you can quantify or separate the whole concentration. So this is how you can
Okay.
say that the whole reaction is going on. I'll share you a video of it. There is a video which is
Okay.
actually telling this.
Okay, and in the case of substoichiometric analysis, it means that all the reactant is consumed at the end,
Hmm.
but some of the all the reagent is consumed at the end,
Hmm.
but some of the second reactant or the target material that is in excess because it
Yes.
has not reacted.
Yes. 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 Exactly.
And in is there anything called a suprastoichiometric wherein the reagent is not in excess but the target items are in excess?
That I'm not aware of. I need to look of it, but that's a good thing. I have heard about this sub-isometric because generally we add this in known amount. We keep the reagent generally in the higher thing because we are going to analyze that only, na.
Okay. And it is similar to like, having a lean mixture in few in automobiles.
Yes, 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 exactly, exactly. Now
You-
you're exactly hitting the right point. You're exactly hitting the right point.
Understood. So
Yeah.
it's like lean and rich mixture of
Yeah,
air and fuel.
yeah, yeah, yeah.
Okay.
Did you read this? You're in bachelor or masters?
Bachelors.
Okay, so there is a this diffusion coefficient and all this partition coefficient, all these things you read in a solution chapter, homogeneous solution where you calculate the homogeneity and all.
Yes, that was yes that I had studied when I was in 12th grade.
Yeah, yeah, no, no. In detail, you will read more. There, you will
Okay.
find it out that how this stoichiometric analysis can be used. It is there. You will read it. But I
Okay.
I have not heard about anything supra stoichiometric till now. But I'll look into it. I'll write to you.
Okay.
Yeah,
Apart from that, I had also sent a few requests to you to allow me to access the files on Google Drive. That
I
is a
allowed,
presentation.
allowed. I allowed already.
Okay. Okay.
Yeah.
Sure.
Okay, so we are moving forward. We are moving forward with the questions, and the first question is the radiochemical separation holdback carriers are used to. They are used to minimize loss during separation, keep unwanted element in raffinate, precipitate the unwanted element in priory, and complex desired element before separation. Do you know the answer of it, Lakshya?
I think the answer is B. And after you give me the correct answer, I want to understand the meaning of raffinate.
You want to understand the meaning of raffinate?
Yes.
Basically, see, in a solvent extraction, no. When we do the liquid extraction, so a liquid which comes out as an impurity, this is raffinate.
Okay. The liquid which comes out as an impurity.
Hmm.
And how do we classify what can be considered as impurity in that particular case? Does it form a precipitate, or how should we identify the impurity?
Yeah, it forms a precipitate basically. It's a residual liquid which is removed from there at last when you do the solvent extraction.
Okay, understood.
Yeah.
So that means in the solvent, by carrying out solvent extraction,
Yes.
there is there is separation of those two phases, one in the aqueous phase, one in
Yeah.
the organic phase.
Yeah, there could be more than two also.
Okay,
Yeah, but
and correct.
there, but basically we talk about the two, and when the aqueous phase is separated and even the organic phase is separated, there is liquid which is of not our use, which is having unwanted elements or impurities, which is raffinate. So in radiochemical separation, the Holbeck carriers are used to precipitate the unwanted element a priority. A priori means as a priority. Okay.
Okay, but I think the answer should be B because that was what was mentioned in the slide. So can you help me with that?
That I have to look because I myself which slide?
You had shown it to me when you were explaining all the concepts covered during this week. It was in, I think, radio analytical techniques, lecture 32. Mostly, I think it's in that video.
Solvent extraction or radial analysis and mixing.
Yes, solvent extraction.
Mm-hmm. Where is it gone? Yeah, it is here.
Yes. So here, no, not in this one. I think it was mentioned. All of the methods were listed in one slide. I think it is in the beginning.
Mm, this.
Not this one. And one more thing, can you please go back to the previous slide? Yeah, this slide, solvent extraction.
Hmm.
Here it's mentioned that M aqueous plus L organic, reversible Ml organic. So so here M is the metal, right? Radioactive element.
Hmm.
L is the ligand,
Organic.
organic ligand, correct?
Hmm.
And Ml is the complex
Yes, adduct of them.
at
Adduct, ADDUCT.
ADDUCT.
Yes.
Okay, so the complex is called ADAC in the case of radiochemistry.
Yeah.
Okay, and why is the complex organic? It could have been a mixture of organic and inorganic. So,
Not generally. Like we write it as organic only because this organic liquid is in a higher proportion generally.
okay, understood.
Yes.
And what is the main difference between a distribution coefficient and separation factor?
Okay. So how can I say? See, when you were talking about the distribution coefficient and separation factor, it is distribution coefficient. How can I say to you? See, suppose you have this M aqueous and liquid. So in chemistry, the distribution coefficient is the ratio of the solute concentration in extract phase to the concentration of the raffinate phase, basically. So you have this
So it
C
is
organic.
similar to the partition coefficient.
Yes, exactly, the partition coefficient. And the separation factor is the ratio of the distribution coefficient of the two components. So basically, this is a ratio of distribution coefficients, the separation factor.
Okay,
Yeah, and it depends on mainly the nature of the solutes or the stationary phase and mobile phase in liquid chromatography, basically.
understood.
Yeah.
Sure. Thank you for the explanation. And you can continue for the for that particular field. I'm trying to search for it.
Yeah, no, I'll myself search it and I'll give you the right answer. I may be wrong because these are the answers that are given to me from sir side. So I will have a look over it. Okay.
Okay.
Okay. The second question is isotopic exchange with preformed precipitate is one of the methods for fast radiochemical separation of what? Cesium, zirconium, uranium, or TC. So it could be multiple answer also. Do you know the answer, Lakshya?
No, I'm not sure about this.
It was mentioned in one of the slides directly. This was TC and CS. Have a look over that in isotopic.
Okay, sure.
Yeah. So the next question is which analytical method is used for separation of the individual rare earth elements from a mixture? We had a lot of
I
this.
think yes. I think this the answer is C. Ion exchange.
Okay. See, the answer could be C also, and the answer could be yeah. The answer is C basically, right?
Okay. And also for the previous question, I think in the assignment we only have the option to choose one element.
Acha, do we?
Yes, but in the but you're given two answers. So I think which would be the fastest is I'm not sure
Cesium.
about that.
You go for cesium. No, no,
Okay.
you go for TCM. TC 99 is basically the most one. TC 99. Yeah. You go for TC. I'll talk to sir.
Uh, okay. And however, there is no option of technetium in this in the list of the possible answers.
Then you go for cesium.
Okay.
Yeah. Next one is which radio analytical method can be used for the determination of blood volume? We
It is B,
yes,
isotopic dilution method.
exactly. This is isotopic dilution method. I have written the answer right, but the option wrong. Okay,
Yeah.
so relative method of neutron activation analysis obviates the need for the determination of which quantities: cross section, neutron flux, detector efficiency, saturation factor, or decay correction factor.
Mm.
You can open the slide of neutron activation analysis.
Okay. Because I had read through this, I had watched this lecture 2 days back, so I don't exactly remember.
Hmm.
Just 1 minute.
Basically, it is a measurement of gamma rays emitted from a sample, which was irradiated by neutrons. So,
Correct. I
uh,
think the cross section will play an important role.
yes, yes, definitely.
That is
So,
one thing.
and the rate at which the gamma rays are emitted from the element is directly proportional to the concentration of the element also.
Okay. Just a few seconds.
I mean, because I'm saying this is depending on, because it's a neutron activation analysis, won't the neutron flux also affect it?
Matter, yes.
Yeah. What about the detector efficiency, saturation factor, and decay correction factor? These are the technical terms. The answer is this: cross section is right, neutron flux is right. The third one is detector efficiency. They do not bother.
Okay.
So you open the NA instrument, and then there you can find about these three techniques, like which amongst them actually affects the determination by NA
Okay.
technique. This two is obvious because these are on the principle. This is
Yes.
instrumental. Okay.
Understood.
Now dysprosium and europium have the lowest detection limit in neutron activation analysis, owing to what? A direct question.
I think it is because of the high neutron absorption cross section.
It could be. Let's see. So yes, it's right because gamma ray abundance will not be there, and if there is a neutron high absorption cross section, then only
Yes.
there could be a lowest detection limit in the NA. Which this is the most feasible, and most plausible explanation of the lowest detection limit of any element, of any radioactive element.
Understood.
Which element is essential for human health but its deficiency can excess result in disease of skin and nails respectively? Right now we discussed.
Selenium.
Yes, definitely. Going to the next question: which ion beam analysis technique is best suited for determination of hydrogen impurity in materials?
I think it is RBS,
What is RBS?
Rutherford backscattering.
What happens in that?
So we are able to measure the angular distribution of the ejectiles.
Hmm.
But I'm not completely sure.
So basically, if I could tell you, no, it's Rutherford scattering is also known as the high energy ion scattering spectrometry. So what
Okay.
happens in an RBS? There is a beam of high energy ions which is directed at a sample, and the ions
Okay.
lose energy, and when they collide with electrons, and sometimes they also collide with a nuclei. So when the positively charged ions approach the nucleus of an atom, the nucleus repels them. So only the backscattered ions are detected. So the energies of backscattered particles are measured, and these energies depend on the identity of the atom, the angle and the depth, all these things that we were talking. So how in what thing they are used? They are used for analyzing the composition and the contamination levels. Also the thickness density, or you can say elemental composition of a complex material. And the what is the best strength? The best strength is it can also be used for a low atomic number element sensitivity, like hydrogen measurements. It can use for conductor and insulator analysis, and it is non-destructive, and it is quantitative without using any standard. So that is why this is
Okay.
one of the important. You don't need to have any standard. It is non-destructive. It is used for low atomic number element sensitivity. So yeah, this is Rutherford backscattering.
Okay. It's NRA or Rutherford? Okay.
Oh, wait, I think I wrote the answer wrong. For low jet matrix, this was an RBS. It is sure. Okay.
Yes.
This one is hydrogen impurity. No, this is also RBS. I need to check it. I need to check it. Which one is right? Now I'm myself confused.
I think the answer is B, ERDA, because I checked in the slides and it is mentioned that for low Z materials, it's a good, low Z impurities, it's a good, so ERDA is employed.
No, for low jet matrix and impurities, RBS is employed.
Okay, because here it says determination of low Z impurities, including hydrogen, in high Z matrix,
This one.
ERDA.
But this is high jet impurities and low jet matrix.
Correct. No, I was talking about the previous one.
This one. Yeah,
Yes, for this it should be
this.
ERDA.
Okay, I'll give a check. I think I'm myself confused. I have to check the slides. Okay,
Yes.
this is RBS for sure. And then the question is, which two elements are taken as a markers for gunshot residues?
Barium and antimony.
Yes, that's right. So I think that's all. So we are confused for two questions. The first one is this one, and are you? And one more was there, no? No,
Um,
no.
it was a determination of just a minute. Yeah, it was regarding which element,
Just
because we can't choose two
yeah,
options.
yeah, yeah.
We have
Okay,
to.
yeah.
So there is a competition between technetium and cesium.
Okay, okay, makes sense. So I'll get back to you with this. Okay, I when I upload the slide, I'll correct it.
Sure,
Okay, then if you have any confusion, you write to me. I'm not well. I'll cut the class today. Next time we can have a good discussion.
sure, definitely.
Okay then. See you, Lakshya. Bye.
Sure. Thank you very much. Hope you have a speedy recovery.
Yeah, yeah. Thank you. Take care. Bye.
Sure. Thank you.